When we perform chemical reactions, we need to quantitate the concentration of our solution. So here you have a solution, it has a solvent, and for us the solvent is principally going to be water for all of our solutions. But then we're going to have solutes, and those solutes will have some concentration in units that we call moles per liter. And moles per liter of solution is a unit that we call molarity. And so that's what we're going to focus on right now, is the concentration of solute particles per liter of the solution. So it's the most common unit for concentration, molarity. It's got a capital M for a symbol, and it's simply moles of solute per liter of solution. So we'll do a division, we'll get a number, and this will be our concentration in molarity. So mixing a solution, how we do that. So in some fashion, you'll have a solute, and that solute's mass of solute will be measured on a balance, and you'll get some gram mass for that solute, and you're going to transfer that to what we call a volumetric flask. And that volumetric flask is a very precise piece of glassware. There is an etch mark somewhere up here, can't quite see it, and you will fill this up with solvent. In this case, H2O will go in here, and you'll fill it right up very, very carefully to this mark. Make sure all your solute dissolves, and you'll be able to calculate the molarity of your solution based on having grams of solute. This will be grams of solute divided by the molar mass of your solute, which will be in grams per mole, and that will be divided by liters of solution. And from that, you will get the molarity. So that's what we're going to do right now. So let's just say you measured out 15 grams of sodium chloride, and you're going to dissolve that solid in a sufficient amount of water to prepare 500 milliliters of solution, and we want to know what the molarity of that solution is. First thing to remember is that you want X moles, in this case, of sodium chloride. And so we'll go ahead and get that. We've got 15.0 grams of NaCl. We need to find the molar mass of NaCl, which is going to be 22.99 grams per mole plus chlorine, which is 35.45 grams per mole, and that's going to give us approximately 58.45 grams per mole. And we'll go ahead and we'll calculate the number of moles of sodium chloride we have. So that's going to be to 3 significant figures. That gives us 0.257 moles. We need to determine how many liters of solution that we have, and that's going to be and they're telling us we need 500 milliliters, so that's going to be 500.0 milliliters, but we need to convert that to liters of solution. So how do you convert milliliters to liters? You divide by 1,000 milliliters per liter. The milliliters cancel, and that gives you liters. Really, you're just moving that decimal place 3 places to the left, so that'll give us 0.5000 liters of solution. And then we can go ahead and calculate X moles per liter for our sodium chloride, and that's going to be 0.257 moles of sodium chloride for 0.5000 liters. We'll have 3 sig figs in that, and that gives us 0.513 molar of sodium chloride solution. That's molarity. Now, let me show you the easy way to do this. I'm going to go straight to moles per liter. I'm going to take my 15.0 grams of sodium chloride divided by my 58.45 grams per mole, and then I'm just going to divide that straight by 0.5000 liters. And if I do that serially in my calculator, 15 divided by 58.45 divided by 0.5, I come out with exactly the same answer, 0.513 molar. And that's the easy way to do that. Let's talk about dilution. Dilution is something you might be familiar with. Back in the old days, we used to have break rooms in companies, and they'd make carafes of coffee in a Mr. Coffee machine. So you'd have this big carafe of coffee. Somebody'd make probably a second or third pot around 10 a.m. in the morning, and then it would sit there. And as it sat there on the hot plate, the water would evaporate. So you would go in at about 3 or 4 in the afternoon to get a cup of coffee, and there would just be this ugly, gooey stuff sitting on the bottom because this had been cooking since 10 in the morning. So here's what you do. You get yourself a little coffee cup, and you pour a little bit of that gooey stuff into your coffee cup, and then you add H2O. What you are doing is you are diluting the concentrated stuff. So whenever you dilute, you add volume and you lower concentration. Okay? And we do the same thing in chemistry. Your reagents come to you in very concentrated forms, but that may not be the concentration you need for your particular chemical reaction. So this is a very specific and precise way to do it. This is a volumetric pipette. There's a little bulb up here that you're using, and you'll suck up about, in this case, not about, but precisely 25 milliliters of concentrate. So you have an initial concentration, a high concentration, but you suck up a low volume. And then you transfer that to a new volumetric flask. So you have the low volume but high concentration. And then what you do is you add solvent, in this case, water. So you add a bunch of water, and you can see that this has a lower concentration, but it has a higher volume. And you can do this very precisely by controlling the concentrations and volumes in your calculation. So what we're going to use is a formula, and it's called the dilution formula. It's just a process by which solvent is added to reduce the concentration of a solution. What you need to remember is moles before the dilution equal moles after the dilution. So here we have a specific number of moles. So this number of moles before the dilution is equal to the number of moles after the dilution. So these two right here, these two are the same number of moles. Okay? And then we're simply adding solvent, and that's going to dilute the solution. All right? So moles before equals moles after, and we can calculate that using molarity times volume. So let's think of it this way. Moles is moles of solute per liter of solution, and I'm using SOLN for solution. And then we're going to multiply that times the volume in liters. This is liters of solution, and that's just over 1. Well, when I do that, liters cancels, and that gives me moles. So moles before equals moles after, and that gives us this equation. The initial concentration times the initial volume will equal the final concentration times the final volume. And what you want to remember here is that this is a high concentration times a low volume, which is going to be equal to a low concentration times a high volume. And the moles in this case equals the number of moles final. And these are equal to each other because the high concentration times the low volume is equal to the low concentration times the high volume. So let's go ahead and work a simple problem. Right after we answer this question, the addition of water to an aqueous solution will result in a higher volume and a lower concentration. Our answer. Okay, so what would the concentration of the solution prepared by diluting 15 milliliters of 12 molar HCl to a total volume of 150 milliliters? All right, you always know what the V1 is because V1 will be the lower volume. You always know what V2 is because it's going to be the higher volume. Okay, so lower and higher. That means that if this is the lower volume, it's associated with the higher concentration, and so what we're looking for is the lower concentration. This would be M2. So we'll just write down the formula. M1 V1 is equal to M2 V2. This is just the initial concentration times the initial volume is equal to the final concentration times the final volume, and this is what we're looking for. The initial concentration is the higher concentration, that's 12.0 molar. The initial volume is the 15 milliliters, that's the lower volume, and this is in milliliters, and then equals to M2 times the final volume, which is the higher volume, 150.0 milliliters. Now, some people would like to ask the question, why don't I have to convert to liters? Well, you could convert to liters, but you'd have to add an extra step to your equation, but you really don't have to do that if the volume is in the same units on both sides. Now, if one of them's liters and one of them's milliliters, you have to change one of them in order to solve the problem. So in this case, we're just going to divide both sides by V2, which is 150.0 milliliters. This guy's going to cancel. I'll do the same thing over here, 150.0 milliliters. Milliliters will cancel, and what we'll come out with here is M2, and M2 in this particular case is going to be 1.2 molar. It is a lower concentration but a much higher volume. Now, you now have 150.0 milliliters of the lower concentration 1.2 molar.